Hi everyone, I'm Charlie Munford and this is Agential Topics. Agential Topics is sponsored by Agential Biology Institute, which is founded because we think there's a missing causal layer in biology that gives cells an intentional direction as they develop, and we're building the infrastructure to study that missing causal layer. So, Agential Topics is where we get together and try to surface in this conversation the best ideas that are out there about cognition and agency. And today we're welcoming luminary Karl Friston, author of The Free Energy Principle. And he has a few words to say, and then we'll have a discussion.
Thank you. Um, Let me share my presentation and then explain why I'm doing a presentation. I think that would be
Okay. I think it should have permissions all
yep.
set. Great.
Right. So I had, well, first of all, let me say it's a great honor to be able to present to this group. It's also a bit intimidating after witnessing the last discussion. So I just want to remind you, I am a physicist and psychiatrist with no foundational training in cell biology, evolutionary theory, or philosophy. So if you can be gentle and understanding with my responses to your questions, I would appreciate that. Um, I had anticipated on after discussion with Charlie not doing a presentation, but I think there was some agreement that perhaps it would be useful to scaffold the discussion with a brief 20-minute presentation. Um, so what I've done is prepared 20 slides, picked out from a number of graphics that could guide the conversation, but specifically to address several questions that Charlie sent me and an additional question that Stuart asked a couple of weeks ago. So I'm going to go through this presentation, just covering the themes that would be useful to address in relation to the questions that were asked. So I'm going to go through it very, very quickly, without not in any depth, but just to put out there the different applications of the free energy principle that might be usefully referred to in terms of answering the specific questions. So I'm going to go through the statistics of life, the role of Markov blankets, with a special focus on scale invariant applications of the free energy principle under the renormalization group, because I think that's going to be relevant for some discussions, and then a couple of applications in relation to natural selection and action selection in cognitive science and ethology, and then just returning at the end to the importance of scale invariance and their relationship to dissipative structures. So when a little box appears in this beautiful pale green, that's a question from Charlie, cut and paste from an email that I hope to be able to speak to. So the free energy principle is effectively a variational principle of least action that gives rise to a particular mechanics, and that's going to be called a Bayesian mechanics, that has as its commitments exactly the same commitments as quantum, statistical, and classical mechanics. The only distinguishing thing is that careful attention is paid to the notion of self in the spirit of self-organization, self-assembly, self-information, self-organized criticality, and so on. And that's usually, or it starts with the notion of a Markov blanket that enables one to individuate the states of self from the states of everything else. And this is borrowed from the work of Judea Pearl, where that separation or individuation rests upon a conditional independence between some internal states and some external states, say the rest of the states of the universe, when conditioned upon a Markov blanket. And I'm going to further divide the Markov blanket, or the Markov blanket is further divided into effectively inputs and outputs in the sense of the sensory states and active states that are operationally defined in terms of parents and children. So the Markov blanket is defined in terms of the parents, the children, and the parents of the children, and the sensory states influence the internal states, but are not influenced by the internal states. And similarly, the active states are influence the external states, but are not influenced by the external states. And with that partition, we've got a definition of self in terms of the states that constitute a particle, person, or population, internal states, if you like, exchanging with external states bidirectionally, but in a particular way through the Markov-Blanket states, the sensory active states. My favorite example is the brain, where the brain can have all sorts of internal states, influences its actuators, or autonomic reflexes and active states that change the external states that could be the body, that then reciprocate by changing the sensory states that in turn influence the internal states. So you've got this circular causality in play, which usually is in the treatments I present is read in terms of a sort of action perception cycle of a particular kind. And then I normally ask people to forget about the Markov blanket, and then we just rehearse basic physics, and then put the Markov blanket back into play to see what kind of mechanics emerge. And the physics that is usually rehearsed is the starting point of most of physics, which is basically a random dynamical system or a Langevin equation expressing the dynamics, flow, or rate of change of states as some lawful function of where you are in phase or state space, plus some random fluctuations. And then from this, we can interpret the trajectory or path through state space as a probability density over the states given the system in question, say me, conditioned upon me. And then the argument goes, well, we know a lot about the density dynamics in terms of the rate of change of this probability density in and of itself. And I've expressed that here in terms of a Fokker-Planck equation, could also call it a master equation or a time-independent Schrodinger equation. And because the systems of the kind that we're interested in keep revisiting the same state that they were always in, otherwise the state would just diverge off into infinity. We know that the probability density in and of itself does not change with time, which means that the Fokker-Planck equation, the density dynamics, has a solution. And that solution is really interesting. It allows one to express the dynamics of any system that possesses this pullback attractor or characteristic set of states in which you find it, in terms of a flow on the gradients of the log probability given the system in question. Interestingly, this flow can be subject to a Helmholtz-Hodge decomposition, and separated into some basically orthogonal flows, a gradient flow on the log probabilities as the system, if you like, counters the dissipative effects of random fluctuations, and an orthogonal solenoidal or curl flow, which I think may be relevant for our arguments. So first question, walk me through this. This is from Charlie. Walk me through the strange loop. I am a prediction of what happens around me, in part because of my predictions. Is that it? Yeah, absolutely. But in an even simpler sense, we start off with strange loops, in the sense that when this solenoidal component becomes state dependent, this path or trajectory becomes chaotic. And it means that although we keep revisiting neighborhoods of states we were once in, because those are characteristic states of the thing that I am, we never actually repeat or revisit we never tread in the same river twice. Furthermore, it means that these kinds of systems will necessarily show oscillations, biorhythms, life cycle, reproduction. It can be no other way. So at any scale, what we're talking about are systems that have this sort of recurrent kind of aspect endowed by this Helmholtz decomposition. It also, to a certain extent, in a slightly naive way, answers Stuart's question, where does novelty come from? Well, the very fact that we're dealing with these strange attractors means that in the future of any trajectory, everything is novel because we've never been there before. So baked into this formalism is a really trivial kind of novelty, but it's a very constrained novelty because we are dealing with systems that have characteristic states or an attracting set, technically a pullback attractor. That's just a slide just to lend intuition to this decomposition into gradient flows down the Planck hole here, and the solenoidal or circular flows that have to accompany this in any non-equilibrium system. So yeah, so that's another this one view of strangeness, in that we are implicitly dealing with systems that have stochastic chaos, where the chaotic aspect rests upon a strange attractor. What is what about the Markov blanket? So what we're doing now is putting the Markov blanket back into play under this very generic formulation of self-organization to these pullback attractors on non-equilibrium steady states, and observe that this decomposition applies to all partitions of that Markov blanket partition, including the internal states and the active states. But by construction, by just individuating or differentiating self from non-self, by construction, these gradient flows do not depend upon, or the gradient flows of the internal active states do not depend upon the external states. They only depend upon the blanket states, and more specifically the sensory sector of the blanket states. So now we've got a mechanics that can be read as perception and action at some level, whereby it will look as if the internal and active, sometimes called autonomous states of anything, say me, will look as if it's trying to gradient ascent or climb or increase the log probability of the sensory states conditioned upon me, the system in question. And this, I think, is, or is often sold as just a unifying formalism that many people would recognize from different perspectives, and I put a few here. So what is the log probability of the sensory states conditioned upon me? It's just those sensory exchanges with the world that have value for me, in the sense that they characterize the kind of sensations I would expect to have. They are literally part of my attracting set, and therefore they are valuable. And from this, you can interpret this as a statement that underwrites things like reinforcement learning, optimal control theory, or in economics, expected utility theory. The negative of this is known as surprisal self-information, or more simply surprise, and via the Feynman-Jensen bound, it's a thing that it is upper bound by a variational free energy. And this can be read in a number of different ways: the Infmax principle, minimum redundancy principles, or maximum efficiency principles, and of course the free energy principle. The average of that free energy or self-information is entropy, the time average, which means it looks as if the internal and active states look as if they're trying to minimize, on average, the entropy. And of course, that's the holy grail of self-organization, as exemplified by synergetics. And if I was a physiologist, it's just a statement of homeostasis. It's just keeping my essential variables within bounds that then maintain my integrity, in the sense that I'm limited to my characteristic states. And if I was a statistician, I would interpret this as something called Bayesian moral evidence. Basically, the probability of these sensory data given me as a model of how those data were generated. And from that, you can appeal to things like the Bayesian brain hypothesis, evidence accumulation, and predictive coding, and the like. So, Charlie's question: what is the opposite of the consequences of the FEP? What would a self be like if it maximized free energy? So the answer to that question is it wouldn't be a self. In fact, it wouldn't exist. Because the free energy principle is basically individuated from its environment and possesses a Markov blanket. It can always be read as minimizing free energy. So if it didn't minimize free energy, then it could not exist. So the free energy principle is a somewhat tautological description of self. It's just a way of describing self-organization by appealing to the existence of these conditional independencies and therefore the sort of teleological reading that you put on top of it. The FEP solves a grounding problem in a different way. Significance is rooted in surprisal, not in survival value, right? How does an evolving self-replicating system come to care about surprisal rather than survival? Are these two goals ever at cross purposes? No. By definition, stipulatively, the surprisal is just the negative value. By definition, stipulatively. So they can never be at cross purposes. They are the same thing, just inverted. An example here, just to give you an illustration of self-organization, where we just simulated lots of macromolecules all coupled in ways where we have Markov blankets that determine the interaction or individuate each macromolecule. But the objective here was to find another Markov blanket at a higher scale in terms of unpacking ensembles of these macromolecules in terms of this particular partition to demonstrate the emergence, spontaneous emergence of a little sort of viral particulate thing here, a little virus with a little cilium here, internal states, blue, active states, interestingly, underneath the sensory states that are pushed into the external states, just to demonstrate the emergence of this kind of self-organization. And I show that example just to illustrate that there are Markov blankets at different scales, and then ask the question, how do you jump from one scale to the next? And this is, I think, a really interesting question, which actually speaks to a deeper question, which is what is a state? And the argument pursued in sort of fuller treatments of the free energy principle sort of follows the following construction. So what's a state? Well, now we've defined something in terms of Markov blanket, we can say that the state is an eigenstate of a particle's Markov blanket. Why? Well, because that's the only thing that I can see from the outside. I can't see, because of this conditional independence, what's going on in the inside. I only need to see the outside, the Markov blanket, and I can summarize the state of a particle by the principal eigenstates of the Markov blanket. But in order to define the state, I've implicitly defined a particle. So what's a particle? Well, a particle is a set of blanket and internal states at the lower level. And then what is a state? A state is, and so on, all the way down. So there's if you like, you elude the question, what is a state? Or indeed, what is a particle and what is the state of a particle, by recursively going to finer, smaller and smaller scales, or conversely going to higher and higher scales. And you can formalize this in terms of the renormalization group, in terms of regrouping and reduction operators. So I can start off with any particular scale. I can partition this into blanket states and internal states, and then I can take move to a higher scale and then take the eigenstates of that and reduce the dimensionality and then just start again. So to generate increasingly higher scales through using the apparatus of the normal group, implying that there are Markov blankets and Markov blankets and Markov blankets all the way up and all the way down. And here's just another illustration of this. One thing that emerges from this analysis, which I think is potentially interesting, as you do so, you through the reduction operator, you effectively throw away fast fluctuations that are on the inside and the internal states when you sort of group things together at the scale above. So effectively, the dynamics of systems, as you increase their scale, also slow down. So by construction, the scales at a higher level, more coarse-grained scales, have more deterministic and slower dynamics than fast fluctuating smaller scales, and that I think is going to be relevant later. So one application of that, which is a more serious addressing of Stuart's question about novelty as it emerges, say, in an evolutionary context. One application of this renormalization group formulation or application of the free energy principle at different scales would be, on some readings, an account of the link between an extended genotype and phenotype in theoretical biology or evolutionary theoretical evolution, where you can think of slow dynamics at an evolutionary scale um, as Markov blankets of certain kinds that prescribe constraints on faster phenotypic states that both are conforming to exactly the same principles, but at different levels. And it's interesting in this instance just to think about this in terms of top-down and bottom-up causation that couple the scales together, so that the genotype, if you like, at the higher level specifies, say, epigenetically, the dynamics and the characteristic sets and the implicit attractors for the evolution of a phenotype at a high scale, but the likelihood of or the negative free energy or the marginal likelihood or the model evidence we talked about before, um, in that scores the quality of this phenotype living in this particular context, now subtends the bottom-up causation in terms of the grouping and averaging that you get in terms of the population dynamics. So on this view, if you come back to the fact that at both levels, you're never quite revisiting exactly the same state. There's in virtue of this stochastic chaos. When the stochastic chaos is read at the genetic level, you will get novel phenotypes. Um, um, and that will be another instance, and I think a slightly more interesting answer to Stuart's question about how do you explain the emergence of novelty? Well, it's just a free energy minimizing process, or if I invert that, a Bayesian model selection process where the model selection rests upon the Bayesian model evidence read as natural selection to produce different things. Kate she has been a former guest and may attend the meeting and has criticised the FEP for being able to apply to pendulums, crystals, etc., which she argues erodes explanatory power. Is this so? Um, I don't think so. I think you have to that worry goes away when you realize there are different kinds of things that are specified by the influences among the different kinds of states that constitute the Markov blanket partition. And one can imagine this, for example, if the active states were an empty set, you would have a good model of a crystal and possibly a pendulum. And one can, I'm not going to do this, but one can certainly work through different permutations and arrangements of these dependencies that underwrite the notion of self or a thing, and generate a whole ontology of different kinds of things. But one which is particularly interesting in relation to novelty of a different kind is if I were to take this sort of this is the minimally sparse dependency structure that would admit a Markov blanket, but I can make it sparser. And if I focus on one particular sparsification, it's the link between the active states and the internal states that would be appropriate if I was dealing with multicellular organisms or large things that have a sort of deep hierarchical structure. So they got Markov blankets in the inside, which means that the internal states now are not directly influenced by the active state. So if I remove that arrow, something very interesting happens. If we can always read the internal states as effectively inferring the causes of the sensory states, if the internal states don't have direct access to the active states, then the active states become a vicarious cause. And that basically can be cartooned as follows. So it now looks as if these sort of larger, deeply structured systems, things, cells, look as if they're inferring their own action. And that allows you now to describe, should you want to, the self-organization of big things with this deep kind of structure as um, planning in terms of planning as inference, as if they're inferring and planning, showing a kind of intentional behavior simply because it looks as if they're thinking about the consequences, trying to infer what they're actually doing. So there's now a divide between the actual real variables, the active states, and the random variables that are being inferred under this what is known as a generative model. And that introduces an interesting twist here because now we have to take the variational free energy functional and apply it now to active states. And this induces something called an expected free energy, or the free energy that I would expect if I committed to this course of action. So I'm basically now trying to tell a story about action selection and a different kind, a different natural kind that would not be, could not be, that is sort of more expressive and more like me relative to a crystal. What is this expected free energy? Well, it's something that endows behavior with an intentional aspect, a motivational aspect. And many people argue that it is necessary to be an agent in the sense that you are actually selecting among different paths into the future that renders you agential in an authentic sense. So here the question, you argue that some organisms are more agential because their predicted time horizons are longer, which means the loop includes counterfactuals. Are there really any living organisms that have a time horizon of zero? I think that's an excellent question. And it really begs, so it gets to the heart of what is an agent in this formalism. So an agent in this formalism would be something that has beliefs about its own action. But notice that in order to select the right action, to infer the right action, it has to know the consequences of its action, and those consequences live in the future. So the implicit generative model has to be future pointing. So it has to include these counterfactuals. And Charlie's absolutely right that the temporal horizon, the depth can vary, but just having a future in mind or an implicit future in mind, I think, is a necessary condition to be an authentic agent. If you had a time horizon of zero, you would be a thermostat or a virus, which would be one step up from being a crystal. But you wouldn't have any intention or motivated behavior because there would be nothing to select. You're not selecting among counterfactuals that underwrite your action selection or policy selection. And the other way novelty gets into the game here is that when you look at the functional form of these energy functionals that underwrite or describe the action and perception. I won't go through this, but just to highlight the fact that there are different interpretations. A statistician would like this kind of interpretation. A machine learning person would like this kind of interpretation. But these different ways of expressing these the free energy functional is nice because you can now think about the corresponding teleology or interpretation when you take the expected value of these under what you think you will experience or see or sense in the future if you did action A. And interestingly, the complexity and accuracy become risk and ambiguity, and these two terms become intrinsic and extrinsic value. I just wanted to focus on that because if I ignore the extrinsic value, the value that these sensory outcomes have for me, my prior preferences, then this intrinsic value is known as Bayesian surprise in the visual search literature or mutual information in expectation. But it's more interesting because it basically scores the epistemic affordance in terms of the information gain. So it is the quantity that describes expiration. It is the, if you like, the part of the imperatives or motivations or descriptions of an apparently motivated behavior that talks about information-seeking behavior and novelty-seeking behavior. So baked into this formulation for and only for certain kinds that have this large, deep hierarchical structure, you will have necessarily a novelty-seeking aspect to it. Just for interest, if I remove different bits of uncertainty, we come up with things like path interval control from engineering or sensitive control from economics. And then finally, if I take all uncertainty off the table, we end up with expected utility theory and sort of pragmatic accounts of goal-directed behavior. So walk me through the solution of the dark room problem. Why doesn't it apply to agency? By definition, if agents are those things whose behavior can be described in terms of minimizing expected free energy, they are necessarily maximizing the expected information gain. Why are they? Why does this preclude the dark room problem? Because the first thing I do in a dark room is to switch on the light, because that has minimizes my uncertainty, because it maximizes my information seeking capacity. So that's the action that I would do. So the epistemic affordances offered to me will immediately take things like me out of a dark room. Finally, just come back to this scale invariant thing, which I think is interesting. So this is more for the sort of physics as opposed to the agential biology at hand here. But I think it's interesting in that it nicely relates to things like Prigoghine's treatment of dissipative structures. So I've just situated now the Bayesian mechanics I've just been talking about in a series of different mechanics that you get as you go from the very small to the very big. And if you recall earlier on, I was saying that as you go from lower scales to higher and greater or larger scales, the random fluctuations tend to get averaged away and things slow down. And that, from the point of view of this Helmholtz decomposition, means that this gamma, this gradient flow, is progressively suppressed as we go from the small to the big. So in the limit of the quantum scale, we have no solenoidal component because it's completely dominated by the random fluctuations. And in that context, you can treat the Fokker-Planck equations as a time-independent Schrodinger equation and then elaborate quantum mechanics from that. If I have lots of things together, then I've now got statistical mechanics that can be articulated in terms of fluctuation theorems and the like. But as I get bigger and bigger and bigger, the balance, there's a Goldilocks regime in which the dissipative and non-dissipative parts, the gamma and the Q, or the solenoidal parts, start to play together. And that's the regime in which the free energy principle is most interestingly applied to biotic kind of self-organization that has this sort of Bayesian mechanics when I put the Markov blanket into play, giving you the self-evidencing and Bayesian mechanics. But if I go too far, I get too big, the random fluctuations go to zero, and I'm just left with the solenoidal dynamics, and that was just Newton's laws of motion, classical Lagrangian mechanics. So when I get to the scale, I summarize dynamics in terms of the position of the moon and the sun and the earth, or large massive bodies, then there is no intentional or agentic behavior anymore, because we've passed through the scale at which there is an admixture of dissipative and non-dissipative dynamics. And that sort of nicely fits in with Prigoghine's sort of early observations. Only when a system behaves in a sufficiently random way may the difference between the past and the future, and therefore irreversibility, enter its description. Yeah, and then sorry, these are questions I hadn't found a slide to address. Has anyone successfully built an inactive FEP robot, and what's its personality like? Um, so the strict answer is well, no. People have built robots based on the FEP, but they don't have much of a personality. They just own fridges and things. However, it is applied in the context of computational phenotyping and psychiatry to try and apply the free energy principle or active inference to a digital twin, and then twiddle or tweak the parameters and the prior beliefs of the digital twin so it reproduces the same behavior of in an experimental context as your patient. And that basically means you can now phenotype or characterize your patient in terms of their prior beliefs. So in a sense, it's sort of phenotyping their personality in terms of what a priori they believe in a very limited situation. That limited situation is, if you like, prescribed by the experimental paradigm, the economic game, or the choice behavior you're trying to elicit that you can actually build a generative model for. But it has been, there have been articles written about how you could apply this to revolutionize robotics, and there is interest in sort of interactions between different agents that do involve sort of affective, valence, emotional, and possibly personality-like traits. So I've been talking incredibly quickly, and the font hope that that's 2 minutes per slide. That's 40 minutes I've been talking. I'm sorry about that. But anyway, these are the people whose ideas I've been talking about. And of course, thank you very much for your attention. I'll stop my sharing.
Wonderful. Thank you so much, Carl. That was so incredibly efficient and illuminating. My goodness. And thank you for so carefully going through my questions. If I had known you were going to take them so seriously, I might have thought about them for a lot longer. But anyway, that was really beautiful. So we'll have a question and answer now. I want to let you guys know that Carl has to go at a quarter to the hour. So we only have a little bit over 60 minutes to discuss. So and since he's already included the answers to Stuart's questions and my questions in his presentation, I'll sort of put myself and Stuart at the end of the line as far as questions. So the way to do this, guys, is to click on the bottom of your screen under React and raise hand, and that'll just put you in the queue to ask a question. And remember that you're typically muted when you're not talking. So when you start your question, be sure and unmute yourself. And after you finish your question, I will probably mute you again. So if you have follow-up questions, try to keep them to a minimum so more people can talk. But it's inevitable. So just try to be efficient. And thank you guys so much. Off we go. I have Henry Hing.
Oh, hi. So I really enjoyed the talk. So you mentioned that the different scale, you actually use the same formula in terms of mechanism, right? For example, you use all the same uh, Markov blankets as the intermediate for different level of thing. However, as we know in the uh, biological system, when the divided into different level, the actually is not a simply self-organization principle anymore, because maybe during evolution at the very beginning, that played a very important role. But as soon as this biological process is established, so the constraint is kicked in, the constraint is a biological process, right? So you do not need every time to emerge, and you just follow simple biological rule. So in that case, so-called I like the constrained novelty. Actually, constrained novelty is not happen at the system level constantly, only in the event of macroevolution occur and be selected upon. So the rest of them is no longer evolutionary problem. I keep emphasizing this point because they become biological problem. So I would like to say, we know biologically they have different law, but maybe the physical law is the same. So that's my question.
Right, that's a challenging question. I think the simplest response is that the free energy principle is trying to equip the natural sciences with a sort of physics of biological systems that should also obviously entail evolution. But just to pick up on a couple of important points, so you're absolutely right. The formalism, the functional form of the dynamics is exactly the same at each level. So that's a requirement of the renormalization group, that you've got the same functional form for the dynamics or the same Lagrangian at each and every level. It's just applied at different scales. So that's absolutely crucial, which means that you are compelled to describe the biological processes that subtend evolutionary development with using exactly this formalism. So I wouldn't draw a line between the variational principles that underlie self-organization and the biological mechanisms and principles that you were describing. I would hope that the physical description in terms of these variational principles is apt to describe exactly the processes you describe. And sort of I can't remember all the details of your question, but sort of one interesting aspect of that is that the way that the phenotype behaves in relation to its eco niche has consequences for the level above, and that that is read under this sort of application of the renormalization group as meaning that the free energy, the negative free energy, or the pathogen of it, can be equated with the model evidence or the marginal likelihood. So you can now read the model evidence, which is a characteristic of this particular phenotype here, as a likelihood that you will find it in this particular eco niche. And when you read it like that, then the you can read it as adaptive fitness, and that means that it will now contribute to the gene pool in proportion to its marginal likelihood, which is going to be in proportion to its model evidence, which is going to be in proportion to the path integral of the free energy principle. And then what that means from the point of view of evolution, what evolution looks as if it's doing, if I was a physicist or a statistician, is effectively doing Bayesian model selection, read as natural selection. And one way you could put a teleology on that, should you want to, which means that basically this evolutionary process is basically seeking evidence for the kinds of phenotypes that exist in its environment. And it does so just by hypothesis testing and accumulating evidence in the phenotype that this is the thing that is most likely to be found in this environment. So that would be one example of a mathematical story that I am hoping would be sufficient, or at least would accommodate a more mechanistic or teleological take on the biological processes. Does that make sense? Is that what you were?
Yeah. Thanks. Yeah. I will ask later on the question. Yeah. Thanks.
Okay.
Great, Mary.
Hi, thanks. Thanks
Yeah.
so much for this really stimulating talk. My question has to do with the correlation of your work with Deakin's absential causation. In active inference, nested Markov blankets are coupled statistically with higher levels inferring the hidden states of lower ones, but biological levels seem coupled to material leaks, cell leaking CO2 biophotons, exosomes, and tissue is organized around what the cell cannot close locally. So this looks to me like Deakin's absential causation, the higher level is shaped by what the lower lacks. And as opposed to the Bayesian influence over hidden states. And I'm wondering if the Markov blanket formalism claims these are equivalent, or is it agnostic about the physical substrate of the coupling? Thank you.
Right, yeah. I did say I haven't got any foundational training in philosophy, so you may have to unpack some of those some of those concepts. Uh,
Well, basically, sorry, I've written the 9 requirements of a holon, a biological holon, and one of them is that they all have leaks and lacks. They have the lacks that Deacon describes, but then they also leak, and that coupling is what uh, allows each level of the holon um, to fill in what it's not able to create on its own, what it's not able to close on its own. I hope that makes it simpler.
right, a little bit. Well, I'm clearly going to have to read a bit more to give you an informed answer to that question. But certainly the filling in. I was muted there. Prevent an echo.
That was my fault, Carl. I'm so sorry. I messed up.
No problem. Yeah. So the filling in it does certainly remind me of the role, or one way of describing Bayesian inference, in the sense that if you've got the internal states of anything, it could be a sort of the internal states of a mitochondria, it could be the internal states of a cell, or it could be the internal states of a brain at different scales. We'll certainly do a filling in terms of optimizing its implicit beliefs about the outside of or the other side of the Markov blanket, the hidden states that are hidden behind the Markov blanket, through this process of inference to the best explanation. I mean, I'm being very teleological and anthropomorphic here. But you can certainly read self-organization at any scale as doing a kind of filling in that inherits from having a compressed representation that has the greatest evidence in relation to the data. And that interpretation inherits from the fact that the log of the evidence can always be expressed in terms of accuracy minus complexity, if you remember one of the slides, which basically means that the best explanation, the best phenotype, or the best sort of intracellular dynamics is that which provides an accurate account of the sensory states to which it is exposed, but as simply as possible. And part of that minimization of complexity and part of that simplification means that you've now got a compressed representation that effectively can be used to fill in. But I've got a horrible suspicion that's got nothing to do with the filling in that you're talking about. Could I, so who is it, Mary? Yeah,
Yes.
could I ask you just to really dumb down and so just ask your questions if you're talking to yeah, to your children.
I
And
always
I'll
have to
stop.
rewrite my questions in what I call 7G, seventh grade, for myself. So here it is. My question is, um, uh, you do a mathematical modeling of the relationship between the holonic levels, the nested levels of the Markov blanket. I see that every level, every holonic level in life is lacking things, and it's leaking things. So, and again, this relates to Deacon. So, for example, in a tissue, like the lung tissue, it's leaking carbon dioxide, but it's also lacking certain nutrients that come from the blood. And so I see that every holonic level has both leaks and lacks, and it's only able to maintain um, a, a closure in terms of its agency if it has things coming into it and it's contributing materially and also thermodynamically, and it's also contributing to the other levels. And that I see this as the coherence between the holonic levels. And I was just wondering how that relates to the mathematical modeling of the relationship
Ah,
between the
I,
levels. That's it.
oh, I understood that. That was brilliant. Thank you very much. All
Sorry,
right.
sorry about that. I think I get a little over enthusiastic about the language when it could be simple.
Right. No, no, it's always good to learn the right words. No, well, in a sense, that is the role of the Markov blanket. So,
Mhm.
very often I think people conceive of the Markov blanket as some sort of insulation that
Yeah.
isolates you from the world. It's not. It is the interface. It is
Yeah.
exactly though that sort of structure that allows for exactly the sort of the leak and the lack to be mediated by a bidirectional exchange across the
Right.
Markov blanket. It is exactly that. And if I was reading the dynamics from looking at it through the lens of thermodynamics, this would entail an exchange of energy and entropy across the Markov
Exactly.
blanket. So, the Markov blanket is not something that carves things and separates things. It's something that glues something together with
Right.
exactly. So, in a sense, the bipartition of the blanket into active and sensory states is exactly this
Yes.
complementary lag and yeah, leak.
And I'm glad you brought up thermodynamic because it seems like it works in, materially, energetically, mathematically, and in terms of prediction, which brings in Rosen.
Good. Yes, I mean, one way of articulating the that Helmholtz decomposition um, is in terms of Bayesian filtering, which is the most popular instance of that is actually predictive coding. And then you get into the whole world of predictive processing. So there's
Yes.
a really intimate relationship. I mean, I repeat, these are sort of teleological interpretations that, where you are committing to a particular teleological interpretation of these dynamics. And the dynamics are just what they are. Um,
I'm
but
all for teleology. I believe that one of the nine requirements is conatus or desire. So have
ah,
at it.
got another two good words there. But I did recognise those, and of course that speaks to the expected free energy and that's why we call them prior preferences. We
Exactly.
shouldn't really, but that's exactly what novelty seeking.
Nice. Awesome. Thank you, Mary. Richard?
Thank you. This is great.
Thank you, Carl. You know how sometimes when you're watching something on YouTube and you think this is going a bit slowly, so you put it at 1.5 times speed? When I listen to the recording of the presentation that you just did, I'm going to be looking for something that slows it down by a factor of 10 so that I can take that in. Um, I was interested in um, understanding a little bit better the potential symmetry between the inside and outside of a system. Um, in one of your answers to Charlie, you said that if a system wasn't trying to minimize free energy, or perhaps you didn't quite say it like this, but if it wasn't successful at minimizing free energy, uh, it would, it's as though it wouldn't be a self, which means that the identity of the blanket would not be stable, right? That the blanket wouldn't be what you thought it was, which seems like it's another way of saying that um, there's a dynamics here where systems find selfhood by allowing their blankets to move until they find a place where the blanket is stable, until they find some sort of symmetry between inside and outside, where they're doing a good job. The inside is doing a good job of modeling the outside, which must mean somehow that the outside is also doing a good job of modeling the inside, that there's a symmetry there. And that's the position where the blanket is stable and the self is a self. And before that, the self is in transformation, right? That not just that the insides are changing, but the identity of the self is changing. And that symmetry, if I'm right, it's a sort of a different way of a different starting point, a different turning the story inside out. Instead of saying, imagine that you have a self, what does it want to do? It wants to model the world. It wants to make things predictable. Another way of thinking about it is imagine that you have a system with parts that are in relationship where the identity of one part, self and non-self, is not yet stabilized. And what happens in that system is that the relating finds an interface of symmetry. Is that an equivalent way to think about what you're saying? Have I got the right end of the stick?
Yeah, no, absolutely. And in fact, if I was trying to explain the free energy principle at that level, I'd certainly start with the second. That would be the preferred, the preferred one. So, I mean, the free energy principle, it's almost tautological. In what it says, it says if something has attained a certain kind of synchrony with everything else, then it can be described as behaving like this. It can be described as seeking evidence. It can be described as having preferences. It can be described as predicting. It can be described as self-evidencing. It's not saying that to self-evidence is the reason. It's not saying that to survive you have to self-evidence. It's just saying that things that survive are defined in terms of can be described as self-evidencing. So I prefer the sort of the more deflationary aspect. When I say I prefer, it is easier, I think, to motivate that perspective. And just to sort of celebrate your sort of notion of this symmetry between the inside and the outside. There are multiple ways we could talk about that, because if that's right, as you are trying to predict and understand and model your environment, the environment is trying to predict and understand and model you, and you get into things like desire paths and niche construction, and then you sort of put other things like me into the niche. So the niche now is actually all things like me, and then you get sort of cultural niche construction, and more importantly, a move from a generalized synchrony or synchronization of chaos between of an asymmetric sort between me as an individual and an environment that doesn't look like me, to an identical synchronization where you are my environment and I'm your environment. So very much at the moment, we are in discourse. You're my world, I'm your world. And we are sufficiently similar in our sort of generative models and phenotypic construction and have a very well-defined Markov blanket, courtesy of Zoom, that we can now find our free energy minimizing solution. So if I was talking to somebody who didn't know anything about self-organization or Bayesian statistics, what they would read from that is that you are finding you're finding the dynamics that are collapsing onto the synchronization manifold. So that would be a dynamical systems perspective on the symmetry and the synchrony that you're talking about. So technically a sort of generalized synchrony or synchronization of chaos that lives on the synchronization manifold. That is the free energy minimizing solution. So after a period of time, then we will come to synchronize, and we will establish that synchronization will be on the Markov blanket. This manifold that sort of separates us, but also joins us in some fundamental way. So from that perspective, if you just integrate any set of random differential equations, introducing sufficient symmetries between the inside and the outside, you will get exactly the synchronization of generalized synchrony and indeed identical synchrony almost that we are currently engaging in. So, we are in conversation, and apart from the turn taking, we're actually rehearsing exactly the same narrative as I try to understand you, and you try to understand me, and then we communicate it. So we are in synchrony in some sort of, at many, many, many different levels. The final point, which I think your question speaks to, is this notion of transience, that we have to find it. We're not just given the Markov blanket, job done. We come into being, and at some point we cease to exist. So the Markov blanket is always in flux from the point of view of the level above. So from the point of view of the scale above, Markov blankets come and go. There is no ergodic steady, there is no ergodicity, and there is never a truly non-equilibrium steady state. It's never attained. By the time you get towards it, you've disappeared. You've literally dissipated. So the failure to look as if you are self-evidencing just means that the Markov blanket has dissolved. That just means you are dissolving, being absorbed gently back into the universe. You've ceased to exist as something that can be disambiguated from the universe. And that happens at every scale, all the time, to everything. So, as I was talking to you, I'm sure I've lost about 230,000 postsynaptic specializations in my frontal lobe. But that doesn't matter from the point of view of my brain or me. But from the point of view of evolution, of course, I'm only going to last for a blink of an eye, the few decades that I'm allowed. So we all come and go. These Markov blankets form and dissipate, and form and dissipate. So it's only while your Markov blanket is in play and you are identifiable as having characteristic states in virtue, which you have to have in order to have the Markov blanket partition, that these rules apply. When they don't apply anymore, you have to move to the next scale just to talk about what is conserved. But just to
So if it's the case that at a given level of organization, the relationship between agent and environment finds a kind of generalized synchrony, when you have a nested system with many different levels of organization, my intuition is that those nested levels, in order to talk to each other in a meaningful way, to not just be noise to one another, that they would need to be harmonically related to the frequencies at other levels. Does that match your intuition too?
Yes, but in here now we will have an asymmetry as you move from one scale to the next scale.
Yeah,
There's certainly and literally the imaginary part of those eigenvalues that I talk about when you do the eigenreduction for the renormalization group operator. They are literally the frequencies. They determine the frequencies of the harmonics. But you only retain, when you go to the higher level, the slower ones. So
right. It's not just that the higher levels are slower frequency, but that there are particular multiples of the wavelengths you had at the other levels.
yeah, they are literally linear. Well, they're locally linear mixtures of eigenvalues that literally are. Yeah, absolutely. But yeah,
Brilliant.
when you apply the renormalization group, you truncate the harmonics, if you like, or the eigen functions, so that you're just retaining the principal ones that have these slow frequencies and slow time constants that don't dissipate quickly.
Right.
Plus, the rest of them have very large negative real parts, which means that they disappear almost immediately from the point of view of the scale above. So they become random fluctuations. So all that's left are these slow harmonics that are the sort of the eigenmodes of the system at that level of description. Yeah, absolutely.
Excellent. Thank you.
That was beautiful. Okay, Wayne.
Hey, Carl. Thanks for giving us this talk. There's a million questions I could ask. I'm just going to go to one of the ones I put in the chat. I'm wondering, are you familiar with Robert Wilson's work in anticipatory systems and life itself, and perhaps some of A.H. Louis' derivatives of that, where he sort of clarified things and went a lot further along the same lines? And do you think, how do you think FEP and active inference might fit into that framework? And do you think they're compatible?
Right. Again, you're going to have to forgive me. One of my mentors, Jerry Edelman, once called me an intellectual thug because of my lack of scholarly background. So I don't I know a lot of things, but only about a limited set of domains. So I'm not absolutely sure what you're referring to, but I did pick up on the words of anticipation, and certainly that would be a central pillar of the predictive processing reading of active inference that can be attributed to these more deeply structured kinds of phenotypes or multicellular organisms or particles in general. And So if it's, well, perhaps you could do me a favor. Could you just sort of summarize what the main insights were from this literature
Right.
that?
So, I mean, Rosen made a bunch of very impressive arguments. So, in anticipatory systems, he sort of derived what properties a system would have to be able to anticipate. And so he came up with something he would call Rosen complexity, uh, where your system is going to be self-referential, for instance. So it's not going to be amenable to computation, for instance, right? So Turing computation would fail for an anticipatory system. In life itself, he makes some deeper claims based on some category theory arguments and his MR systems, but I don't think I want to really go into that because it's going to end up being perhaps too much
Right. No,
given the
it's all right.
time.
I now recognize Rosen. Yes. No, I have come across Rosen before, and I don't know his work deeply, but I do remember thinking at the time this is exactly right and entirely
Yeah, me too.
consistent with the with the free energy principle. And I also remember thinking, in fact, I thought then this is also very reminiscent of early cybernetic formulations of things like the good regulator theorem and the law of requisite variety that sort of echo this. And I think that the interesting thing you just said there, that this can't run on a Turing machine with the sort of and the self-referential aspect, of course, the whole argument I was trying to make about what defines an agent or what is agency. It is having a generative model of the consequences of my actions. So it's implicitly self-referential. It's not your actions, it's just my private future. And I've got a model of my private future, which is quintessentially anticipatory in nature. So that particular aspect of self-evidencing in these deep structured things seems exactly consilient with Rosen's notions. And why can't it work on a Turing machine? I think that's an interesting thing that
Well, the
could be.
halting problem, right? I mean,
Yeah,
really, you get endless loops.
yeah. And there is an orthogonal argument, which is much more sort of dull-minded, but practically possibly an interesting one. That sort of Turing machines are exactly the kind of thing that can't exist under under a natural science formulation of the kind that the free energy principle aspires to, in the sense that you've got sort of infinite memory and infinite compute and the like. So it's a beautiful construction. I'm thinking here of things like universal computation and the like, Solomon induction. I mean, it's a beautiful mathematical thing, but the whole point is you can never realize that in reality when you actually look at self-organization in real dissipative structures. So that's certainly one.
Yeah, when I was
Another.
the physicist who made this kind of argument, he was actually critiquing Roger Penrose's book on his strong argument against strong AI, and his argument was that he actually does a lot of coding because he's a I think he's a QED physicist, and he said you could never actually construct one of these things. He did a whole talk on this that it's great, it's a great theoretical argument, but you actually could never construct this thing. Couldn't be done. Not for the reasons that you outlined, because he didn't have that to work with at the time. It's just 30 years ago, maybe. But
it reminds me of the, the wonderful thing about sort of my understanding of I repeat universal computation or current excitement about taking this algorithmic complexity to its limit in terms of that it is uncomputable. So people talk about universal computation, but by definition, it can't be computed. So that always makes me smile. But But there's another interesting take on that, which is due to Geoffrey Hinton, which is a notion of mortal versus immortal computation. So his argument here is that the software of the kind you could run on a von Neumann architecture, and potentially a Turing machine, is immortal in the sense that it can be run on every machine. But of course, that's not an apt description of real life computation or agents in generic in general, in the sense that they are examples of mortal computation, which he would read as substrate dependent. So the computation is in the substance, is in the substrate itself. So when you switch off the mortal computer, it dies. You can't switch it back on again tomorrow.
Yeah, this is like Levin's polycomputing type of thing. Yeah. To me, my view is that computation in the Turing sense, at least the finite Turing sense, is one of the things that living systems can do. What we've done is we've abstracted that, and we're sort of reimagining that as the only thing they do, which that was kind of what Penrose's argument was also, is that what we do is more than Turing computation. What type of computation it is, we can't say, at least yet.
Nice. Thanks, Ryan. Yeah, that's wonderful. I just want to make sure I don't miss anyone. Alicia, did you have your hand up?
Oh, go ahead. Have Stuart ask his question.
Okay. Yeah, Kate and Stuart, you guys are up next. Thank you.
Hi. I was the one with the hand up because you put Stu to the back of the queue, but I'll share. Karl, I want to say it's such a delight to meet you. The more I understand your language and what your model is saying, the more I realize that you are a common kindred spirit and one of my new heroes. However, when I first encountered your stuff, I was kind of horrified because I've been studying the emotional system for 40 some years, and one of my big beefs is emotion is pretty much missing from everything. So I always thought that any kind of machine metaphor, even one as good as a computational metaphor, is still a machine metaphor. But this one is really pushed right up against exactly the kinds of differences that we experience as embodied agents, fully embodied agents. So I've backed off on I still think that it's too neurocentric. I still think that it's ignoring all of the deep embodied interoceptive processes that come from the bottom up in terms of stochastic this and that, but it's much more orderly than that. What I want to say is I came at your work through Mike Levin's work, and I'm wondering how the concept of bioelectric fields that are kind of synonymous with what Markov blanket, how you're rooting that maybe in quantum field theory in terms of the fact that the Markov blanket has internal information and external information. So that's one of my questions, but my most important question has already been raised by, several times, and it's the question of identity. The idea of self as an automatic, self-generating this or that is great, but the concept of identity, I think, is really important here because the Markov blanket is essentially the partition, the boundary between internal and external. So I think that there's extra work that can be added on based on what the emotional system is doing. And I'd love to talk to you about it someday. But for now, I want to talk about resonance and brain waves, because if we're going to look at the brain, let's do it. So you talked about how the slow wave eigenstates are kind of the reference point. And in my work, I talk about that as the resonance at the edge of chaos and how we're actually perceiving these things and participating directly through our emotional sentience, what I call the self-regulatory sense. So my question for you is about the various brain waves and how the theta wave, which is the very slow, actually when we're sleeping or when the mind is dipping into the unconscious, if you will, that has been associated with emotion. And it's also been associated when it's disconnected from the gamma frequency with psychiatric disorders. So that's the pointed question I'd like to ask you about how this jibes with the psychiatric dimensions of it. But I really would love to talk to you sometime about how emotion and valence in particular can enhance this model and make it more lifelike. Long
Right.
question.
Yeah, yes, I could spend an hour unpacking that question. So many intriguing aspects to it. I don't want to. I won't jump to the specific the last question, because I think it's worthwhile just re-emphasizing the importance of emotional inference and interoceptive inference. And I think, if you got something like a Neil Seth, to one of these sessions. So Anil Seth would be like me, but is much more sort of beast machine invested in the interoception and the embodiment aspects of it. But at the end of the day, he would still, I think, be appealing if you forced him to the sort of predictive processing gloss on this kind of self-organization, self-evidencing. So I think it's really important that this physics of sentience is not about visual input in a sort of machine learning vision, sort of machine vision context. 99% of the useful information about me comes from my body. So the interoceptive inference is absolutely crucial. And of course, again, if you allow me a sort of teleological description of what's going on, if I am self-evidencing, where I'm going to be looking for evidence is my body. It's literally my gut feelings, because one of the most important things I have to infer is my state of mind at the moment, and that presupposes, of course, that I have the hypothesis or the representation that I am me. But let's assume that I'm sufficiently deep and structured that I have at least a minimal selfhood, and more importantly, a selfhood that has a granularity that allows me to recognize that I am in this state of mind. I am embarrassed. I'm in love. I'm frightened. I want, I'm thirsty. That's not strictly speaking an emotion, but it's Panseppian in its way that it speaks to interoceptive inference and emotions. So, that's probably one of the most important jobs of this self-evidencing, is just to recognize what state of mind I am in, and implicitly all my attentional intentional sets that are now going to color and shape my self-evidencing and my actions and behavior in the future. You also mentioned valence and affective. So there is a little literature on affective inference under the free energy principle, and also emotional inference and interoceptive. And to me, they have very distinct meanings. Affective inference is just, is it good or bad? And that usually reduces to the level of uncertainty about what I'm going to do next. So, there are many sort of probability distributions associated with active inference readings of neuronal dynamics. One of the most important, I think, is basically the belief distribution, the belief structure over what I could do next, from which I have to select. And if I am uncertain about what to do, that seems to be often associated with angst and anxiety and negative valence. And then when suddenly, oh, I know what's going to happen to me, I'm going to have a cup of tea, get a reward, get a fruit juice if I'm a monkey. So I know the future. And of course, that future is conditioned upon what I am going to do. Even if I'm doing nothing, that's still a very active thing that I select. Then that uncertainty resolves and I feel good. And that has a positive valence. And there's an interesting literature coupling that to dopamine release. You can sort of simulate these things. So I'll stop talking about that because that wasn't your question, but I just wanted to acknowledge that interoceptive sources of evidence, and the embodiment is absolutely crucial. You can also apply this this theorizing to the immune system, so it doesn't have to be, you don't have to be neurocentric. You can be you can also be you can look at different parts of the body and tell a similar story. But just to come back to your specific question, the the um, the theta and gamma and brainwaves and frequencies, then that's why I was sort of quite careful to emphasize the role of that Q, that solenoidal aspect, because what that means is you can't have this kind of biotic self-organization without frequencies and all frequencies everywhere all the time. It can't be done. Otherwise, you'd have a point attractor and you'd be dead. You using them, so our frequency is important. I mean, yes, absolutely, because if there weren't frequencies, there wouldn't be, you wouldn't be there. And also these frequencies, in that conversation with Richard, there's a certain nesting which is important, and you're picking out, I think, a really important sort of frequency band, gamma and theta in the brain, which is clearly an important consideration when it comes to things, as you say, like schizophrenia research. I would argue that the theta rhythm is particularly important, though, in a special way. We were talking before about sort of a reciprocal exchange with the environment, and in our conversation, my conversation with Richard, we talked about turn taking. There's a similar kind of turn taking that occurs in active vision, active perception, in the sense that I will act upon the world, I will palpate the world in some way, I will query the world, ping or prompt the world in some way, and then I will listen to how the world responds. And then do my belief updating through this sort of free energy minimizing process. But that seems to have a saltatory aspect that occurs at theta frequencies. So, for example, if I look at the way that I actively sample the visual sensorium through saccadic eye movements, I do that at the theta frequency. If I'm a little mouse, I'm going to sense my world by moving my whiskers at a theta frequency. I am talking where the phonemes are emitted at a theta frequency. I am listening at that frequency. So it seems to be quite fundamental for animals of roughly our size. This seems to be quite a fundamental kind of frequency, which sort of suggests that the gamma frequency is what's happening in between these sense-making episodes after you've moved or positioned your your sensory organs in the right kind of way to gather the right evidence that's going to resolve the uncertainty or respond to those epistemic affordances at every scale, which suggests that you've also got this sort of oscillatory dynamics in the belief updating process itself. And the interesting connection with schizophrenia in my world is that it may score the fidelity or the precision of messages from lower levels of the hierarchy in the brain to higher levels. And most formulations that I'm aware of in terms of predictive coding and the Bayesian brain of schizophrenia is that it's a disorder, if you like, a sort of functional disconnection that is due to a failure to modulate the gain or the precision of message passing amongst different hierarchies. And the link with gamma activity in this instance is that it looks as if that gain depends very much upon the excitation inhibition balance, that in turn depends very sensitively on fast spiking inhibitory neurons that orchestrate and create these fast synchronous exchanges, usually expressed in the gamma range, within which the gamma frequencies are nested within the theta as you do your belief updating, as you sample the world at different levels. So that was a sort of very specific answer to your question, which I hope spoke to your particular interests, but it was also I did manage to slip in a bit of a shout for embodiment and emotional interoceptive processing.
Thank you. I just one final quick comment. Is there positive emotion in your model?
Yeah, well, any resolution of uncertainty would certainly be have a positive valence. In my model, well, in the model when people like Ryan Smith or and others apply this active inference to emotional inference, emotions are then arise as a construct. So there are some people who have, say, a kind of alexithymia or a dyslexia of emotions, and they're just good or bad, and the other people who have a very fine-grained, nuanced representation of self, a self model that then so the structure of the emotions may be very specific to each individual. And the emotion, I repeat, is a hypothesis about my current state of mind, which is something I have to recognize in a James Langian kind of way.
So would it be correct to say that you're saying valence comes from the top down and not the bottom up?
I don't think I'd say that. I think whenever asked these questions, the inevitable answer I arrive at is it's circular causality. I have to recognize I'm in a particular emotional state, which means it's a completely bottom-up process. But the whole purpose of being in this emotional state is that I can top-down contextualize, attend to the right kinds of things, invoke the right kind of sensory attenuation, or indeed act in a particular way. So it's both bottom up and top down.
Thanks. I would love to chat sometime.
Go ahead, Steve.
Can you hear me?
We can.
Absolutely. Yeah.
Yeah. Karl, it's a deep pleasure listening to you. I have begun to understand your work. You've thought so long and so hard and so carefully. You present an integrated formulation that is years of your thinking, and it's going to take me some time to take it in. I want to raise two issues, and I hope I can state it clearly. This is for all of us, Karl, not just you and me. One is the conditions for open-ended evolution. So in the biosphere, life started something like 4 billion years ago on this planet, with first the prokaryotes for many, many, many years, and then we got eukaryotes, then multicelled organisms, and we get redwood trees and tigers and leopards and bacteria and fungi. We have not achieved open-ended evolution anywhere in the field of artificial life that my old friend Chris Langton started. It keeps getting stuck. I think it's getting stuck because it's algorithmic, but nevertheless, we have not. So, in the evolution of the biosphere, in a profound sense, new possibilities arise. And in the evolution of life, we have always had to find new opportunities or new affordances. So we're non-equilibrium, self-reproducing molecular systems. So we have to eat. So to eat, we have to find something in the environment that's useful. And the problem is, what constitutes useful for me? Namely, new relevant variables. So the fundamental worry that I have with what you've done, which I think is wonderful, is you've pre-stated the variables. One begins with a pre-stated phase space, which is exactly the move that Newton makes. One has position and momenta, and one begins with the boundary conditions of the system that define all possible combinations of position and momenta that defines the phase space. Then you have laws of motion among the variables, Newton's laws, and then you have initial conditions. You integrate the laws to get an entailed trajectory. So theme one is that evolution seems to create new relevant variables. Cardiac ejection volume was not a relevant variable 3 billion years ago, but it's a relevant variable now. How is it the case that the evolution of the biosphere creates ever new relevant variables? Question one. Question two, can we deduce the new relevant variables from what the biosphere was 2 billion years ago? My claim is no. So Andrea Rowley and I wrote a paper called A Third Transition in Science. It's Journal of the Royal Society interface April 14th, 2023. And I'll just say it's there if you want to read it. The second issue I want to raise is a different notion of identity. I will not refer to qualia or experiences at all, but let me say it briefly. I think it's useful. So, what is work? Well, it's force acting through a distance. Atkins says, no, work is a thing. It's the constrained release of energy into a few degrees of freedom. Okay, that's fine. Think of a cannon as a boundary condition constraint. The cannonball inside and the powder between the cannonball and the base of the cannon, the powder explodes and you don't get a spherical explosion. The gas escapes down the bore of the cannon and it does work on the cannonball. So, okay, no constraints on the release of energy, no work. And then I, not being a physicist, but I trained in medicine, you may have too. I asked, where did the cannon come from? Well, it took work to make the cannon. Well, the cannon's a boundary condition. This is very strange. Newton's got boundary conditions. He doesn't tell us where it comes from. So no constraints, no work, and at least sometimes no work, no constraints. Somebody made the cannon. I got a little further. Work can construct a constraint. In 2015, Mael Monteville and Matteo Mosio proposed constraint closure. It's a set of constraints that depend upon one another. I almost misheard them, and so I'm going to be very careful. My notion of a constraint depending upon a constraint is that constraint one constrains the release of energy that constructs constraint two. It's not just depend upon. The constraint one is the boundary condition that constrains the release of energy that constructs constraint two. Gonan Ashkenazi has a 9-peptide autocatalytic set. Each peptide ligates two half fragments of the next peptide to make a second copy of that peptide around all 9. The system is collectively autocatalytic, so it's a Kantian whole. The parts exist formed by means of the whole, and it achieves constraint closure at the same time. Peptide 1 binds the two half fragments of peptide 2, therefore lowers the activation barrier for the reaction. The reaction occurs, work is done, a peptide bond is formed. Gonen's set literally constructs itself. I want to point to a new idea, the union of catalytic and constraint closure. I think that's a definition of life. And it's a new union. It's a union of catalytic and constraint closure. The system literally physically constructs itself. There's no notion of experience here, Karl and the rest of us. The Alicia URO, I think, may find this happy. It literally constructs itself. So I think that's a notion of agency and identity without yet appealing to qualia or experience. And the system could be a nonlinear dynamical system. It could be edge of chaos. Therefore, it can categorize its world and act in its world. And I think this system is capable of open-ended evolution because in a Kantian whole, the function of a part is that subset of its causal properties that sustains the whole. The function of your heart's to pump blood, not make heart sounds. But a part that's a physical thing can be co-opted so that other causal consequences come to be of use and a new function. So your heart can evolve to be an earthquake detector. And that's not deducible. There's no deduction of alternative uses of the same thing. And I think that yields for us open-ended evolution. And I think this is probably right, Karl, in all of this. And the question is, in what sense can we mathematize it? And it's not so obvious. So it's a huge whole turf. And I'm fascinated to think how it ties into the way that you have formulated everything you've formulated, which seems just beautiful. I'm kind of puzzled and thrilled to be listening to you. I think that's a comment, but in any case, it's an opening of some kind. Thank you, guys.
Well, thank you. Again, it would take me another hour to respond to all the invitations implicit in that question. I just want to say it's a real honor to speak to you. Before I was saying that Jerry Edelman was calling me an intellectual thug, and to cure me of that, he made me read all the good and greats, including people like Ernst Mayr. And that's when I came across your works. I've always had a bit of hero worship for you, and
Oh
you
gosh,
know,
this is great. Yeah.
this is
We should take one another out to dinner. Everybody else comes along our treat.
So that's your ideas have been underneath a lot of this notion of self-organization for decades now,
Yeah.
in some form or another. Um, in relation to clearly, I can't answer those questions, but I can certainly touch upon the two big themes. Where can you predict where the relevant variables will emerge in the future? In terms of open-ended evolution, and I agree with you entirely. No. Can you and sorry, I'm trying to formulate a paraphrase the second question. How can one mathematicalize? I should just also slip in at the same time that Jerry Edelman was accusing me of being an intellectual thug, he also accused me of having mathematosis, which he used to abhor. You're inviting me to indulge in mathematosis. So the
Oh,
way that I
well,
would indulge in that instance would be as follows. I think that sort of the catalytic aspect and the closure aspect is if you were to write that down in terms of a random dynamical system, or more simply just the sort of differential equations, you're speaking to a fundamental nonlinearity.
sure.
And any sort of any influence of the influence of one thing or another of a catalytic sort basically is a second order interaction. So as soon as you do that, you're introducing high order terms into the
Sure.
dynamics. And if you remember before, I was careful to say that as soon as that solenoidal part of the dynamics becomes a state dependent or second order in the states, you now get biotic kind of self-organization. So the way I'd respond to that is the mathematical space that you would demonstrate, you have to have this catalytic kind of closure in order to be self-organizing in some meaningful or biotic sense, would just be to show that with and without those high order dependencies in the solenoidal part, the non-dissipative part, is necessary to actually reproduce the kind of dynamics that we've been talking about. The closure part and the roller constraints I thought was really interesting as well, but purely from the perspective of a mathematical constraint. So if you wanted to, again, indulge some mathematosis in terms of constraints, what I would immediately go to is the fundamental role of constraints in observational physics due to E.T. Jane. And he brought to the table this notion of constrained maximum entropy and ultimately maximum caliber principles, where the caliber is just a measure of the likelihood of a path through some state space and the like. But the operation, the heavy lifting is done by the constraint. So it's the constraints on the maximum entropy that actually give things their functional form and their shape. And when you write down, so the free energy principle is dual to the constrained maximum entropy principle. But what the free energy principle does is it sort of makes very, very clear what the constraints are. And the constraints just are those afforded by the generative model. And if the generative model implies the existence of a Markov blanket, then it would necessarily then mean that you have the constraints are almost stipulatively required for specification of the generative model, or read another way, the generative model supplies the constraints that define the kind of thing any self-organizing system is. So you can't have a self-organizing system unless you can write down its pullback attractor. Its pullback attractor creates now a probabilistic generative model. That generative model is the constraint that, coupled with the maximum entropy principle, now describes the evolution and the dynamics of the system, at least as it is observed. So I think there are easy moves, whether they're pleasing or satisfying or not is another question, but there are easy moves to accommodate both the autocatalytic and catalytic aspects, closure aspects, and constraints within the maths of self-organization of the kind that people like Prigogine or E.T. James would recognize. Interestingly, also speaking to the previous conversation about oscillations and dynamics, all rests upon this sort of high order solenoidal dynamics that characterizes, which you don't get in 20th century physics. They don't deal with that. They just deal with equilibrium with point attractors. It's only when you get into non-equilibrium physics and self-organization that these things really hit you in the face. So I hope there was something else I wanted to tell you, but I've forgotten what it was now. All sorts of interesting things came to mind. Was that sufficient? The first one. Oh,
Yes.
yeah. No, it's
Karl,
not sufficient. No, I just wanted to acknowledge the unknowability of the relevant variables that will emerge in the future. This is a real thing in machine learning at the moment, and it's basic. Also, I would imagine a real thing in economics in terms of radical uncertainty, just not knowing the space of possibilities. How can you have any uncertainty over a space where you don't even know its support? And
Exactly.
And in machine learning, this is a big thing in terms of causal discovery or structure learning. And it's a really difficult problem because you can't use standard gradient descent to explore a space of possibilities that you've never ever witnessed before, hypotheses that you've never witnessed before. So the structure learning problem is a really outstanding problem. And it's nicely illustrated by the sort of benchmarks that the machine learning AI community bring to the table to show what's the next direction of travel. So there's something called the ARC3 challenge, which is all about basically trying to get machine learning people and large language models to do abstract reasoning, which is exactly exploring things that have never been seen before. The true novelty. And that's it's a really interesting problem. I repeat, you can't solve by sort of gradient descent. You have to move into the world of discrete hypothesis testing and structure learning, in the way that you and I do it as scientists and theoreticians. It's a very deep problem. So I agree entirely. You can't predict the unknown. You just have to wait patiently and admire it when it happens.
Well, this is lovely, and I'm wondering. You have a bunch of people waiting, and I'm just wondering about Alicia Uerrero somewhere back there. If she could say something, this is her turf as well. But other people have their hands up, and I'm not in charge. Charlie, you are.
Oh, it's okay. But speaking of constraints and closure, I promised Karl that we would end at a quarter to the hour because he has another meeting. So I just wanted to, say if Karl, is that constraint still with us?
Oh, I only need 10 minutes. So you want another 6 minutes. If you can do 2 questions in 6 minutes, that'd be wonderful.
Oh gosh, that may be a challenge. But let's give it a try. We've got Henry and Bill in the queue. And yeah. And sorry, and Alicia as well, was in the queue and then was out and back, but Stu just queued you up, so maybe there's something you can say quickly.
I just have a quick question. Would you be particularly upset if I tried to de-tautologicalize the Markov blanket by saying ontologically it's a sort of constraint regime or overarching constraint regime that integrates all the various dimensions of an organism, metabolic, endocrinological, cellular, biological, cultural, and so on, into an overarching constraint regime. And what I find that I don't understand exactly how it works in your view is how does that constraint regime come to be. And my argument would be that you have enabling constraints that are typically the autocatalytic recursive processes feedback operating against a background of context-independent constraints like gravity or the cosmic light cone or whatever, and then they interact such as to create an interdependent constraint regime, but always local and temporary. And Catherine, would you be very upset if I said at other levels of organization, maybe some of those constraint regimes might get tagged? And I'm thinking of emotions and feelings as the tagging. That's a terrible, I feel like I'm copping out, but it's a form of tagging in terms of valence, tagging in terms of feelings that certainly minimizes the surprisal, because all you have to worry about is danger, get out of it, or pleasure, go towards it, that sort of thing. And so it's an emergent property that tags constraint regimes at different levels. Anyway, that's my thought. Would you be terribly upset if I called the Markov blanket a formalization of a constraint regime?
Well, that's an easy question to answer. Not at all.
Ooh, made my day.
I put it in your and I was mindful of your presentation a couple of weeks ago, and how consistent that was with this sort of separation of scales, with the kind of constraints that don't change with time, the sort of the laws that we operate under, and the ones that are, and your mention of sort of the transience, the temporary, that exactly was what I had in mind when talking about the sort of the separation of time scales and the transience of these Markov blankets operating on these contextual constraints. Yeah.
Just to follow up, and the interface, of course, is the embodiment of that Markov blanket that negotiates what gets in, what gets expelled. I wouldn't say lacking and needing. I would say trying to achieve a metastability because it's an open system with matter, energy, information coming in and being expelled as waste or whatever. Thank you.
Yes.
Thank you very much.
Good.
Well, guys, we may have to bring it to a close with Karl, but with a great round of thank you and applause.
Thank you so much. That was incredible.
Thank you very much.
Yeah, and I just want to say, Karl, this meeting is part of basically one long conversation that's been going on for about 2 years, and so I'd like to invite you to be part of that conversation and to come back and join us, just as a participant, and that's how a lot of us have gotten here. So thank you so much.
Oh, thank you. That was wonderful.
And I'll keep the meeting open. So maybe Henry and Bill, we can continue to discuss, those of us who have a few more minutes. And thank you so much.
Thank you all. Bye-bye.
Thank you.
So yeah, I actually just have one quick question, because so according to the FEP model, so we should consider biological system actually is judge them. We are judging the overall capability of use information for correct choice. So if that is true, then they have two issues we need to separate. One issue is the biological system, the capability of process the information, right? Because the environment information in, you make the right choice. But on the other hand, so the so-called information self-contact also very important. So that is the idea of why the species will be replaced, right? So from the bacterial, eukaryotic cell and the multicellular, every time, no matter how successful the species are, they will be replaced. So that actually kind of address the question Dr. Kaufman is asked, is what is the ultimate driving force for the evolution? So we thought maybe is increase the information complexity. That is the major goal of the evolution process. Every time replace different species, because every time they replace, it turns out the system is more complicated. And therefore, they actually have more powerful to predict, to make the choice, right? So therefore, we can say at the very beginning, they have limited this, but with the brain formation, everything that become more, maybe in the future selection, we have much more involvement for this direction. Human may design, we go to Mars, or we can design use a totally different mechanism to support our nutrition system, whatever, for example. So therefore, if that's the case, we really need thinking about how the information contact increase the complexity, whether or not, I want to ask the speakers, he's gone, but we can't send the email. So to how to, to thinking about those ideas, because the simple question is bacterial or human, which one is more effective in terms, according to FEP model, to dealing with, right? Because this is relative speaking, but also is historically totally different. So when people are talking about cognition and everything, we have to come back to the original historical ecosystem rather than what we know right now to imagine how the system is working. Yeah, I will stop here. Yeah. But anyone else, if you have answer, we can discuss.
Well, Henry, I'll offer a partial answer. I wanted to mention this to Karl. We had a paper being refereed, just accepted by Biosystems, talking about the epistemic limits of cellular intelligence. And one of the issues that came up is our application of Markov blankets to help explain those epistemic limits. It's very confusing to a lot of people that Markov blankets are present in all physical entities. And what distinguishes living forms, as you're asking, where's the distinction in the living process? Francesc Belushi and I came up with an idea of a biological Markov blanket. And that links to, discreetly links to the plasma membrane and Kate's comment about biofields, our critical biofields. And that links further to our concept of the genome as a sensory organism of the cell. And so we believe that a biological Markov blanket, a distinct type of subcategory of Markov blanket, distinguishes prebiotic from biotic states. And the key is that the plasma membrane is itself discriminating and acts as the interface, the beginning interface of cognitive selection within the cell. And that is the foundation of the informational complexity that you're talking about, Henry.
Did I understand him correctly to be saying that if he didn't say this explicitly, but I thought I understood that what he was saying, the boundary between life and non-life is just sort of a level of recursion.
Yeah.
Like the degree of recursion, of predictive recursion is what makes.
Yeah, I'm sure that he would have said that. He said something else that's really very important that kind of could easily fly by. A Markov blanket and boundary is a sensory boundary. He made that as a distinct statement. And of course, that caught my eye because we're talking now about a new concept of biological Markov blanket, which is explicitly linked to the cellular synapse, to its actual sensory apparatus, its totality of its ability to sense external environmental cues. And from that, information transits the external membrane as the beginning of this process, and it gets measured internally, from which info computation and valence derives. And so we really have a strong linkage of how living systems work if we make the assumption that FEP is a very useful theoretical construct and it's actualized in biological terms at the level of the plasma membrane as a first interface.
So I agree. I mean, after the first interface, and then they gradually build up, use a different mechanism. That's why, so, for the congregation study, we really need, from the beginning, And gradually, every time the complexity increase and ensured by specific molecular or physiological or evolutionary mechanism as a constraint, every step to fix them up. So we can simply say because the coding become more and more, not the complexity to deliver such a, the accumulated interface as such, if you
I was still a little bit puzzled. He had a pretty direct answer for the dark room problem, and he was saying, well, the predictive system flips on the lights, but I I know it's super basic, but I'm still puzzled by that because to me, flipping on the lights is kind of a metaphor for acting on the world to make it less predictable. Right. And so if you're if you're a system that's seeking a predictable world or a predictable environment, and he even said, natural selection is Bayesian model selection, which I think was a really clear articulation of it. Um, if you're acting on the world to reduce uncertainty, there's still a sort of counterfactual there. There's a um imagination of what might be possible if the lights were on. That seems at variance. If you leave the lights off, you'll never discover, but you'll live in a more predictable world. So that leaves me that in some ways it leaves me with a deeper question than I had before the meeting, I think. Anyway. Oh, guys, we're almost to the hour. So I just want to thank you guys, and I'll go ahead and turn off the recording if unless anyone else has a burning comment or question. Alicia? Oh, you're muted. Sorry. You're muted, Alicia. I'm sorry. You're muted. Let's see.
I'm just saying thank you. I need to leave.
Oh.
I'm sorry. Thank you. Thank you
Yeah.
so much. See you
That
next
was
time. Thank
wonderful.
you.
And thank you, Alicia, for
Bye-bye. Thank
joining
you.
again.
Thank
Yeah,
you.
great. Okay, guys. Bye-bye.
Thanks, Charlie.
Let's see.